Did you know there's a planet where it rains diamonds? Not just tiny specks, massive, glittering diamonds tumbling from the sky like celestial hail. That's just one of the countless cosmic secrets hidden in the vast, mysterious expanse of space, waiting to shatter everything you thought you knew. The universe is far stranger, more beautiful, and more unpredictable than any textbook could ever capture. And today, we're diving deep into 30 of the most jaw-dropping space facts you've never heard, facts that will make you question reality, spark your imagination, and leave you staring at the night sky with a whole new sense of wonder. Think about this: everything we learn in school about space is just the tip of the cosmic iceberg. We're taught about planets orbiting stars, black holes swallowing light, and maybe even the occasional supernova. But what about the whispers of ancient neutron stars humming like interstellar lullabies, or the fact that Venus, our so-called sister planet, spins backward, defying the rules of our solar system? The universe doesn't play by the rules we've scribbled in notebooks. It's a wild, untamed frontier where the impossible becomes ordinary. And that's exactly why we're here, to uncover the bizarre, the breathtaking, and the downright unbelievable truths that slip through the cracks of classroom lessons. This isn't just a list of trivia, it's a journey through exploding stars, rogue planets wandering the galaxy alone, and oceans hidden beneath the icy crust of distant moons. Each fact is a doorway into a deeper mystery, a reminder that we're part of something unimaginably vast. So whether you're a space enthusiast or someone who's just curious about the secrets of the cosmos, buckle up. By the end of this, you'll see the universe and maybe even yourself in a whole new light. Ready to have your mind blown? Let's begin. Right now, as you look up at the night sky, the moon is silently slipping away from us, not in some dramatic escape, but inch by inch, year after year. It's drifting about 3.8 centimeters farther from Earth annually, a slow cosmic retreat fueled by the tug of war between our planet's gravity and the moon's pull on our oceans. This might seem insignificant, but over millions of years, it adds up to something extraordinary. Picture this: 4 billion years ago, the moon wasn't the distant, serene orb we see today. It was a whopping 10 times closer, looming large enough to dominate the sky, with tides so violent they would have drowned entire continents in relentless waves. So why is this happening? It all comes down to tidal forces. Earth's rotation is faster than the moon's orbit, and as our planet spins, the gravitational drag of the moon slows us down ever so slightly. In response, that energy pushes the moon into a higher orbit, like a cosmic game of tug-of-war where both sides lose a little ground. The consequences are mind-bending. As the moon drifts farther, Earth's days will grow longer, not by minutes but by hours. Imagine a future where a day lasts 25, then 30 hours, stretching time itself as the moon's grip weakens. Even tides, those rhythmic pulses of the ocean, will fade, becoming gentler shadows of their former selves. And here's the twist: this isn't just a one-way journey. The moon's retreat is slowing down too. Billions of years from now, it'll reach a point where Earth and the moon become tidally locked, forever facing each other like distant dance partners, never drifting closer or farther apart. But until then, every sunset you watch, every tide that rolls in, is part of this grand, slow-motion farewell, a reminder that even the heavens are in constant, quiet motion. While the moon is slowly drifting away from us, Venus has been spinning in utter defiance of cosmic norms backward. Picture a world where the sun rises in the west and sets in the east, where days stretch longer than years, and where the planet rotates so sluggishly that a single Venusian day lasts 243 Earth days. That's Venus, the solar system's ultimate rebel, turning in the opposite direction of nearly every other planet. Scientists call this retrograde rotation, and the mystery of how it happened has sparked theories wild enough to rival sci-fi. One leading idea suggests that billions of years ago, a colossal impact, perhaps with a Mars-sized object slammed into Venus with such force that it flipped the planet's spin. Imagine the chaos, a cataclysmic collision so violent it literally sent Venus spinning the wrong way. Another theory points to the planet's dense, suffocating atmosphere, which may have created gravitational friction strong enough to gradually reverse its rotation over eons. But here's where it gets even stranger. Unlike Earth, where our magnetic field and fast rotation help protect us, Venus's sluggish spin means it lacks a strong magnetic shield, leaving it vulnerable to the Sun's brutal radiation. Its thick clouds of sulfuric acid trap heat so effectively that surface temperatures soar to 800 degrees Fahrenheit, hot enough to melt lead. Yet Venus wasn't always this hostile. Some researchers believe it might have once had oceans, even continents, before a runaway greenhouse effect turned it into the hellscape we see today. What makes Venus's backward spin even more fascinating is how rare it is. In our solar system, only Venus and Uranus, which rolls on its side like a tipped-over barrel, break the rotation rules. Every other planet spins counterclockwise when viewed from above the Sun's north pole, following the same direction as the original cloud of gas and dust that formed our solar system. Venus didn't just ignore the rulebook, it threw it out entirely. So next time you gaze at the evening star, remember, that shimmering point of light hides a world spinning defiantly against the tide, a reminder that even in the ordered cosmos, outliers and oddballs keep the universe endlessly surprising. Hidden deep in the heart of our galaxy, floating among the stars, there's a cosmic bartender mixing the universe's most outrageous cocktail, a sprawling cloud of pure alcohol nearly 1,000 times wider than our entire solar system. Meet Sagittarius B2, a colossal molecular cloud near the Milky Way center containing enough ethyl alcohol to fill billions of swimming pools. We're talking trillions upon trillions of liters of booze drifting through space, enough to keep every party in human history going until the end of time. Now, before you start dreaming of interstellar pubs serving galactic margaritas, here's the sobering truth. This cosmic bar is strictly off-limits. Sagittarius B2 isn't just alcohol. It's laced with deadly chemicals like vinyl cyanide and formaldehyde, turning what might seem like the ultimate space-age distillery into a toxic wasteland. Even if you could scoop up a glass of this cosmic brew, one sip would be your last. But how does a cloud of alcohol even form in the vacuum of space? It all comes down to chemistry on an interstellar scale. Within these vast molecular clouds, simple atoms like carbon, hydrogen, and oxygen collide and stick together, gradually forming more complex molecules. Over millennia, these building blocks combine into ethanol, the same alcohol found in your favorite drink. The process is slow. Think millions of years, but in the frigid depths of space where temperatures hover just above absolute zero, these reactions unfold undisturbed. What makes Sagittarius B2 truly special isn't just its staggering size or the sheer volume of alcohol. It's a goldmine for scientists studying the origins of life. Complex organic molecules like ethanol are precursors to amino acids, the building blocks of proteins. This means that drunk cloud might hold clues about how life's essential ingredients form in the cosmos before hitchhiking on comets or asteroids to new worlds. So next time you raise a glass, remember, somewhere out there, a cloud 100 light-years across is doing the same, proof that the universe has a sense of humor, even if its cocktails are strictly for chemistry nerds. Cheers to that. Mercury, the closest planet to the Sun, should be the last place you'd expect to find ice, a world where daytime temperatures soar to 800 degrees Fahrenheit, hot enough to melt lead. Yet hidden in the perpetual shadows of its polar craters, tucked away from the Sun's blistering gaze, lie vast deposits of water ice. This discovery flips everything we thought we knew about the inner solar system on its head. How does ice survive in a furnace like Mercury? The answer lies in its peculiar tilt, or rather, its lack of one. Unlike Earth, which tilts on its axis and gives us seasons, Mercury's rotation is almost perfectly upright. This means some deep craters at its poles never see sunlight, creating freezing cold traps where temperatures can plunge to -300 degrees Fahrenheit. These shadowy vaults have preserved ice for billions of years, untouched by the inferno just a few miles away. But here's the real mystery: where did this ice come from? Scientists believe comets' icy leftovers from the solar system's formation played a key role. Over eons, these cosmic snowballs bombarded Mercury, delivering water that froze in the planet's polar sanctuaries. Some theories even suggest hydrogen from the solar wind could have reacted with minerals in Mercury's soil, slowly creating tiny pockets of water. It's a cosmic chemistry experiment on a planetary scale. This discovery doesn't just rewrite Mercury's story, it reshapes our understanding of the solar system's history. If ice can endure on Mercury, then maybe other seemingly hostile worlds harbor hidden oases too. It also raises tantalizing questions. Could these frozen reservoirs have supported primitive life in the past? While that's a long shot, the mere possibility proves the universe loves defying expectations. So next time you think of Mercury as a scorched wasteland, remember, even in the most unforgiving corners of space, nature finds a way to hide its secrets in plain sight. On Venus, time moves in ways that would baffle any Earthling. Imagine celebrating your birthday twice before the planet even finishes a single day. This isn't some cosmic glitch. It's the bizarre reality of a world where a day lasts 243 Earth days, while a full trip around the Sun takes just 225. That's right, a year on Venus is shorter than its day, a paradox that turns our basic understanding of time upside down. Why does Venus spin so agonizingly slowly? The planet's thick, toxic atmosphere plays a starring role. This blanket of carbon dioxide and sulfuric acid clouds isn't just heavy, it's a gravitational drag, creating friction against the surface that acts like a brake on the planet's rotation. Think of it as trying to wade through a pool of molasses while wearing lead boots. Over billions of years, this atmospheric handbrake has slowed Venus to a crawl, making its rotation the slowest of any major planet in our solar system. But the strangeness doesn't stop there. Venus doesn't just spin slowly, it does so backward, a phenomenon known as retrograde rotation. If you could stand on its surface, ignoring the crushing pressure and 800-degree heat, you'd witness a sun that rises in the west and sets in the east, creeping across the sky at a snail's pace. A single sunrise to sunset would stretch nearly 4 Earth months, with daylight lasting longer than an entire season back home. This extreme slow-motion spin has wild consequences. Venus's lack of a magnetic field caused by its sluggish rotation leaves it defenseless against solar winds which strip away its atmosphere over time. Meanwhile, the planet's thick clouds trap heat so efficiently that surface temperatures stay blisteringly hot day and night. It's a world where time itself feels stretched and distorted, a reminder that the universe doesn't owe us logical, Earth-like rhythms. What's truly mind-bending is how this affects Venusian timekeeping. If you lived there, you'd need a calendar where dates change faster than the clock. Seasons would be dictated not by the planet's tilt, which is nearly zero, but by the slow march of daylight across its barren plains. Even time zones would be meaningless. A single sunset could last for weeks. Venus's twisted timeline forces us to rethink how planets evolve. Was it always this slow, or did a cataclysmic collision billions of years ago throw its rotation into chaos? Could a young Venus have spun normally before its atmosphere smothered its momentum? Every answer leads to new questions, proving that even our closest planetary neighbor holds secrets that defy textbooks. So the next time you glance at the evening star, remember, that glowing dot is a world where time itself dances to an entirely different tune. The sun might look like a glowing ball of gas from here, but at its heart lies something far more extreme, a core so dense it rivals the heaviest metals on Earth. Picture grabbing a chunk of the sun's center. Just 1 cubic centimeter would weigh 150 grams, nearly 8 times denser than solid gold. That's like squeezing Earth's entire mass into a sugar cube, an unimaginable pressure that turns hydrogen into the universe's ultimate power plant. What creates this staggering density? It's the crushing weight of the sun itself, a gravity so intense that it forces atoms together with relentless force. In most of the sun, gas behaves like, well, a gas. But in the core, where temperatures rocket past 27 million degrees Fahrenheit, protons move so fast they overcome their natural repulsion and fuse into helium. This nuclear fusion doesn't just light up the solar system, it fights back against gravity's squeeze, creating a delicate balance that keeps the sun from collapsing further or exploding outward. Here's where it gets wild. The core's density isn't just a fun fact, it's the reason life exists. Without that compact, superheated engine, fusion couldn't sustain itself. The pressure has to be high enough to smash atoms together millions of times per second, converting millions of tons of hydrogen into pure energy every moment. That energy takes a long, chaotic journey, bouncing around for tens of thousands of years before finally escaping as sunlight, and gold's density, its child's play compared to the sun's core. A gold bar's atoms nestle tightly, but they're still mostly empty space. In the solar core, particles are packed so tightly they stop behaving like individual atoms, forming a seething plasma where electrons and nuclei move freely. It's a reminder that the universe's most ordinary-looking objects often hide extremes beyond our everyday experience, proof that even a familiar yellow star is anything but ordinary. For over 300 years, Jupiter's Great Red Spot has been the solar system's most iconic storm, a swirling crimson maelstrom wider than Earth itself, raging with winds that scream at 400 miles per hour. But this ancient tempest, once so vast it could swallow 3 planets our size, is vanishing before our eyes. In just the last century, the storm has shrunk by more than half, and recent observations show it's dwindling faster than ever, leaving scientists scrambling to understand why. The Great Red Spot isn't just shrinking, it's changing shape. What was once a towering oval now resembles a crumpled rose, its edges fraying as smaller storms nip at its boundaries. Some researchers believe these baby storms are stealing energy from the giant, like piranhas chipping away at a bleeding wound. Others think Jupiter's jet streams, those rivers of wind that circle the planet, are shifting and starving the storm of the heat and gases it needs to survive. What makes this disappearance so unsettling is how little we truly grasp about gas giants. The spot isn't just a storm, it's a window into Jupiter's churning, chaotic heart. Unlike Earth's hurricanes, which fade when they hit land or cold water, Jupiter's storms have no solid surface to disrupt them. They feed off the planet's internal heat, rising from depths where pressures are so extreme hydrogen turns into a liquid metal. The spot's longevity was once proof of this endless energy supply, but now its decline hints that even Jupiter's fury has limits. Here's the real kicker: we might be witnessing the end of an era. If the current rate holds, the Great Red Spot could vanish entirely within our lifetimes, dissolving into nothing more than a faint smudge in Jupiter's clouds. That would make us the last generation to see this celestial titan in its full glory. A storm that's outlasted empires, revolutions, and the entire history of modern astronomy. But the spot's demise isn't just a cosmic spectacle, it's a lesson. Gas giants like Jupiter are laboratories for atmospheric extremes, and their storms teach us about weather patterns light years away. The spot's shrinkage could reveal how energy moves through these alien atmospheres, or how megastorms on exoplanets might flare up and die. Even in its death throes, the Great Red Spot is rewriting the textbooks, proving that the universe never stops teaching if we're brave enough to watch. Saturn's dazzling rings might look eternal, shimmering like cosmic jewels around the gas giant, but they're actually newcomers on the solar system stage, barely 100 million years old. That means when dinosaurs like Tyrannosaurus Rex stomped across Earth, Saturn stood naked, its iconic rings nowhere to be seen. This revelation shatters the long-held assumption that the rings formed alongside the planet 4.5 billion years ago, forcing astronomers to rethink one of the most famous features in our cosmic neighborhood. So how did these rings appear so late in the game? The leading theory points to a celestial catastrophe, a moon that wandered too close to Saturn and met a gruesome fate. Imagine a world the size of modern-day Titan, Saturn's largest moon, drifting inward over eons until the planet's gravity ripped it apart. The moon's icy shell would have shattered into countless fragments, while its rocky core likely plunged into Saturn's depths. Those surviving ice shards caught in orbit gradually spread out into the dazzling rings we see today. It's a cosmic demolition job on a scale we can barely fathom, a whole world dismantled and repurposed as planetary decoration. But the violence might not have stopped there. Some models suggest a series of smaller moon collisions, like interstellar bumper cars, could have contributed to the rings' formation over time. Each impact would have sprayed ice and dust into orbit, adding to the growing disk. What's wild is that we might be catching Saturn at a special moment, a fleeting chapter in its history. Rings this young are fragile, constantly eroded by micrometeorites and Saturn's own gravity. Without fresh material replenishing them, they could fade entirely within another 100 million years. The real smoking gun for the rings' youth, their brightness. Over billions of years, cosmic dust and radiation should have darkened Saturn's rings, tinting them a murky gray. Instead, they gleam with almost unnatural purity, their ice largely untouched by the wear and tear of deep time. Spacecraft like Cassini confirmed this by measuring the rings' composition, finding them far too clean to be ancient relics. Even their intricate structure, those gaps and braids sculpted by tiny shepherd moons, hints at a system still settling into place, not one frozen in time for eons. This discovery does more than rewrite Saturn's story. It challenges our entire understanding of planetary rings. If Saturn's bling is a recent accessory, could Jupiter, Uranus, or Neptune have sported similar bling in the past? Are we just lucky enough to live in the brief window when Saturn's rings are at their most spectacular? The universe loves reminding us that nothing, not even the grandest celestial landmarks, is as permanent as it seems. What looks like an eternal masterpiece might just be a snapshot, a fleeting sparkle in the endless dance of the cosmos. The universe has its own version of a cosmic blender, neutron stars spinning so fast they could puree entire planets in seconds. These stellar remnants, left behind after a supernova explosion, rotate up to 600 times every second, turning at speeds that defy logic. Picture a city-sized object whirling faster than a jet engine's turbine, its surface moving at nearly a quarter the speed of light. That's not just fast, it's physics pushed to the breaking point. What makes these dead stars spin like hyperactive tops? It all comes down to density. A single sugar cube-sized chunk of a neutron star weighs 1 billion tons, packing the mass of Mount Everest into something you could balance on a teaspoon. When a massive star collapses in a supernova, its core crunches down under unimaginable gravity, squeezing protons and electrons together until they merge into neutrons. The star's original rotation doesn't disappear. It gets concentrated like a figure skater pulling in their arms to spin faster. The result, a pulsar, a neutron star that beams radiation like a lighthouse, sweeping the cosmos with deadly precision. The forces at play here are almost cartoonish. A neutron star's gravity is so intense that if you dropped a marshmallow onto its surface from just a meter high, it would hit with the energy of a nuclear bomb. That same gravity locks the star into a near-perfect sphere, with surface bumps no taller than a grain of sand because anything larger would be crushed flat. Yet despite this unimaginable density, neutron stars spin so fast they nearly fling themselves apart, held together only by gravity's relentless grip. Here's the wildest part: that insane rotation isn't just for show. As neutron stars spin, their magnetic fields trillions of times stronger than Earth's whip around like invisible tornadoes, accelerating particles to near light speeds. These create beams of radiation that flash across space like a cosmic strobe light, earning them the name pulsars. Some pulse with such precise regularity they rival atomic clocks, ticking off milliseconds with unshakable accuracy. But even these cosmic speed demons can't spin forever. Over millions of years, they lose energy, their rotation slowing as they shed power into space. The fastest ones, called millisecond pulsars, get a second wind by stealing matter from a companion star, revving up like a battery recharged by celestial theft. It's a reminder that in the universe's grand dance, even the most extreme objects are part of an endless cycle, spinning their way toward an inevitable quiet. Yet for now, they remain nature's ultimate demonstration of power, concentrated beyond reason, a billion tons in a teaspoon, whirling faster than thought itself. In the endless expanse of space, there's one absolute certainty: silence. Not the serene quiet of a forest at dawn, but a total, suffocating absence of sound, a vacuum where even the most cataclysmic events unfold in eerie stillness. Here's the brutal truth: sound needs molecules to travel, something to vibrate, whether it's air, water, or the hull of a spaceship. But in the void between stars, there's nothing: no air, no medium, no way for vibrations to reach your ears. That means a supernova could detonate right beside you and you'd hear nothing at all. This cosmic silence isn't just a quirk of physics, it's a life or death reality. Take the Apollo 13 mission, when an oxygen tank exploded 200,000 miles from Earth. Inside the spacecraft, astronauts heard the blast as a deafening bang, metal twisting and gases erupting. But outside, radio transmissions captured only the crew's frantic voices: no explosion, no screeching metal. The vacuum swallowed every sound the moment it left the ship. If you'd been floating beside them in a spacesuit, the silence would have been terrifying. A catastrophe playing out in complete muteness, like a horror film with the volume turned off. Hollywood, of course, loves to ignore this. Star Wars gives us TIE fighters screaming through space, and Star Trek's faces roar with cinematic fury. But real space combat would be eerily mute: no engine roars, no laser zaps, just the faint vibration of your own heartbeat in your helmet. Even the death of a star, an event unleashing enough energy to outshine galaxies, would ripple outward without a whisper. The universe's most violent dramas are performed on a soundless stage. So why does space refuse to carry sound? It's all about density. Earth's atmosphere is packed with molecules, constantly bumping into each other like a crowded room passing a secret. But space is emptier than the best laboratory vacuum: just a few stray atoms per cubic meter, far too sparse to transmit vibrations. The quieter the cosmos gets, the more we realize how privileged we are on Earth, where sound connects us to everything from birdsong to thunderstorms. Out there, it's a vast, uncaring quiet, reminding us that the universe wasn't built for human senses. Yet this silence isn't entirely absolute. Some cosmic objects find loopholes. Take black holes, for example. While their collisions emit no sound waves, they create ripples in space-time itself, gravitational waves detectable by instruments like LIGO. Converted into sound, these waves produce eerie chirps, but that's just science translating the untranslatable. The cosmos speaks in vibrations we can't naturally hear, a language of math and light, not sound. So the next time you watch a sci-fi epic with booming space battles, smile at the artistic license. The truth is far stranger: a universe where even the loudest explosions are ghostly performances, playing out in a theater with no sound system at all. Deep in the constellation Cancer, orbiting a star 40 light-years away, there's a world that puts every jewelry store on Earth to shame, a planet literally made of diamond. Meet 55 Cancri E, A scorching hot exoplanet where the crust isn't rock or ice, but layer upon layer of crystallized carbon, glittering under the glare of its nearby sun. Forget mining for gemstones, this entire world is one massive diamond, roughly twice Earth's size, and with a value so astronomical it could crash every economy on our planet combined. What makes this place such a cosmic jeweler's dream? 55 Cancri E is what astronomers call a super-Earth, but with a twist. Its composition is carbon-heavy, meaning it's packed with the same element that forms diamonds back home. Unlike Earth, where carbon is just a fraction of our crust, this planet's interior is so rich in carbon that crushing pressures thousands of times stronger than our deepest oceans squeeze it into solid diamond. The surface, likely a mix of graphite and diamond, with vast plains that glint like a fractured disco ball under its star's relentless glow. Now, before you start drafting plans for the ultimate interstellar heist, there's a catch. 55 Cancri E isn't just a treasure chest, it's a nightmare to visit. The planet orbits so close to its star that a single year lasts just 18 Earth hours, and surface temperatures soar to 4,000 degrees Fahrenheit. That's hot enough to vaporize steel and melt the very diamonds you'd want to harvest. Even if you could withstand the heat, the gravity, 3 times stronger than Earth's, would pin you down like a bug under a hammer. But here's the real kicker, that diamond crust might not even be the weirdest part. Some scientists suspect the planet's interior could be a sea of liquid carbon, a molten diamond ocean churning beneath the surface. Imagine continents of solid diamond floating on a shimmering, superheated carbon sea, a landscape straight out of sci-fi, where the very ground beneath your feet could be a sloshing, glowing soup of liquefied gems. So how much is this blinged-out world actually worth? At current diamond prices, 55 Cancri E's mass could be valued at around $26 million. That's 26 followed by 30 zeros. It's a number so absurd it makes Earth's entire GDP look like pocket change. Of course, economics doesn't work that way. Flooding the market with that many diamonds would instantly make them as worthless as gravel. But that's the irony of the universe. The rarest, most precious substances are often locked away in places we can never reach. The existence of a diamond planet isn't just a fun fact, it's proof of how wildly diverse planets can be. Out there, worlds aren't just variations of rock and gas. They're laboratories of extreme chemistry where familiar elements twist into forms we've never dreamed of. 55 Cancri E forces us to rethink what a planet even is, blurring the line between geology and jewelry. So next time you admire a diamond ring, remember, somewhere out there, an entire world sparkles with a brilliance no human mind could ever match, and it's been doing so for billions of years. When the Hubble Space Telescope launched in 1990, it was supposed to give humanity crystal-clear views of the cosmos, our sharpest eyes on the universe. Instead, the first images it sent back were a blurry, humiliating mess. Stars looked like smudged fingerprints, galaxies melted into fuzzy smears, and scientists quickly realized something was catastrophically wrong. The telescope's primary mirror, painstakingly polished for years, had a flaw so slight you couldn't see it with the naked eye, just 1/50th the width of a human hair. But in the unforgiving precision of space optics, that tiny error turned Hubble into a $2.5 billion nearsighted joke. The culprit, a miscalculation during the mirror's construction. The edges had been ground just a fraction too flat, a mistake caused by a single speck of paint on a measuring device used to calibrate the mirror's curvature. That microscopic oversight meant Hubble's light-gathering surface couldn't focus properly, scattering starlight like a camera lens smeared with grease. Imagine commissioning a masterpiece from the world's greatest painter, only to realize they'd been working with smudged glasses. The implications were devastating. Entire scientific projects shelved, careers hanging in the balance, and NASA, a reputation crumbling under the weight of late-night talk show punchlines. But here's where the story flips from tragedy to triumph. engineers didn't scrap Hubble, they treated it like a patient in need of glasses. The solution: COSTAR, the Corrective Optics Space Telescope Axial Replacement, a set of 5 coin-sized mirrors designed to counteract the flaw. Installing it would be one of the most audacious repairs in history, requiring astronauts to perform delicate surgeries in zero gravity, swapping out components like interstellar mechanics. In December 1993, the Space Shuttle Endeavour carried up the fix, and over 5 grueling days of spacewalks, the crew pulled off the impossible. The moment of truth came when the first corrected images hit Earth. Where once there had been blurry ghosts, now galaxies snapped into razor-sharp clarity, their spiral arms etched with impossible detail. Nebulae glowed with intricate filaments of gas, and star clusters revealed thousands of individual points of light. Hubble wasn't just fixed, it became everything scientists had dreamed of, all because a team refused to accept failure. What's astonishing isn't just the repair's success, but how it transformed Hubble's legacy. That flaw forced engineers to innovate in ways no one anticipated, leading to upgrades that made the telescope even more powerful than originally planned. Later missions installed better cameras, extending Hubble's vision farther and deeper into space. The very accident that nearly doomed it became the catalyst for 3 decades of revolutionary discoveries, from measuring the universe's expansion rate to capturing the iconic pillars of creation in the Eagle Nebula. Hubble's story is a testament to human stubbornness. We launched a broken telescope, then invented a way to fix the unfixable, turning a cosmic embarrassment into one of science's greatest redemption arcs. It's proof that even our most glaring mistakes can become stepping stones, if we're brave enough to keep reaching for the stars. On Earth, we're used to sunsets painting the sky in fiery shades of red and orange, a daily spectacle that feels woven into the fabric of nature. But on Mars, the rules of twilight get flipped upside down. When the sun dips below the Martian horizon, the sky doesn't blaze with warmth, it glows with an eerie, ethereal blue. This isn't some artistic flourish from a sci-fi movie. It's cold, hard science captured in stunning detail by NASA rovers. The secret behind Mars's blue sunsets lies in its alien atmosphere. Earth's skies turn red at sunset because our thick, nitrogen-rich air scatters shorter blue wavelengths of light during the day, leaving the longer red wavelengths to dominate when the sun is low. Mars, however, has an atmosphere just 1% as dense as ours, and it's filled with fine, iron-rich dust particles. These tiny shards act like microscopic prisms, scattering blue light in all directions while allowing red light to pass straight through. The result, a sunset that looks like it's been dipped in liquid cobalt, with the sun itself appearing as a pale, white-blue disk against a dusky pink sky. Watching this play out through the lenses of rovers like Curiosity and Perseverance is nothing short of surreal. The cameras capture the sun shrinking into a delicate sapphire jewel, its light refracted through the dust-choked air. Shadows stretch longer and sharper than on Earth, free from the softening effect of our thicker atmosphere. And because Mars's dust hangs persistently in the air, the blue glow lingers, clinging to the horizon long after the sun has vanished. But what makes this phenomenon even more fascinating is how it ties into Mars's brutal environment. Those same dust particles that paint the sky blue are also responsible for the planet's apocalyptic dust storms, tempests that can engulf the entire globe for months. When these storms rage, the blue tint intensifies as even more dust gets kicked up to scatter light. It's a haunting reminder that beauty and danger often walk hand in hand on other worlds. This celestial color swap isn't just a fun fact, it's a clue. By studying how light interacts with Martian dust, scientists can decode the planet's weather patterns, atmospheric composition, even the potential for future human settlers to predict storms. Imagine standing on the red planet one day, watching that blue sunset while checking your weather app for incoming dust devils. The universe has a way of turning the familiar alien and the alien familiar if we're willing to look beyond our own sky. If you could take a deep breath in the depths of space, which you absolutely shouldn't, you might catch a whiff of something bizarrely familiar: raspberries. That's right, the universe has a signature scent, and it's not the metallic tang of stardust or the sterile void you'd expect. Scientists analyzing a giant gas cloud near the center of our galaxy discovered something unexpected: ethyl formate, the same chemical that gives raspberries their sweet, fruity aroma. But before you picture floating through a cosmic berry patch, there's a twist. Mixed with that fruity sweetness is the sharp, acrid punch of burnt gunpowder, a scent cocktail as unsettling as it is intriguing. This cosmic perfume comes from Sagittarius B2, the same cloud teeming with enough alcohol to fill a galactic distillery. Ethyl formate forms when ethanol and formic acid combine, a reaction that happens naturally in the chaotic chemistry of interstellar space. But here's the kicker: while it smells like dessert, it's laced with lethal companions like propyl cyanide, turning this seemingly whimsical discovery into a toxic no-go zone for any would-be space sniffers. Astronauts have their own first-hand accounts of space's odd aroma. After spacewalks, they've described clinging to their suits, a scent like seared steak, hot metal, and welding fumes. The culprit: atoms from the solar wind, cosmic rays, and traces of ozone clinging to their gear, a residue of the raw, unfiltered void. It's as if space itself leaves a calling card, a burnt, industrial reminder of its hostility to life. What makes the raspberry connection so fascinating isn't just the irony, it's the clue it offers about life's ingredients. Ethyl formate isn't just a fun aroma. It's a building block for more complex organic molecules, the kind that could eventually form amino acids. The universe might be cooking up the seeds of life in vast, fragrant clouds, mixing raspberry sweetness with gunpowder bite in a recipe written billions of years ago. So next time you bite into a raspberry, think bigger. That flavor isn't just Earth's, it's Stardust's, a tiny echo of the cosmos's hidden palate. And if you ever get a whiff of something burnt after a spacewalk, congratulations, you've just smelled the universe's dark, delicious contradiction. Most of us grew up thinking Earth had just one moon, that serene, silver companion we see hanging in the night sky. But the truth is, our planet has been playing host to countless hidden guests, tiny cosmic hitchhikers that briefly swing into orbit before vanishing back into the void. These are minimoons, asteroids no bigger than a car that get temporarily captured by Earth's gravity, becoming fleeting, unofficial satellites. Take 2006 RH-120, a near-Earth asteroid about the size of a small house that spent nearly a year orbiting us in 2006 and 2007 before slipping back into solar orbit. What makes these minimoons so fascinating isn't just their stealth, it's how they revolutionize our understanding of near-Earth space. Unlike the Moon, which formed alongside Earth billions of years ago, minimoons are interlopers, often remnants from the asteroid belt that wandered too close. Their orbits are chaotic, pulled between the competing gravities of Earth, the Moon, and the Sun, making them drift in irregular paths that can last anywhere from a few months to several years. Detecting them is like trying to spot a speck of dust caught in a whirlwind. Only the most sensitive telescopes stand a chance. The scientific value of these tiny cosmic nomads is immense. Because they're so small and spend so little time near us, they've remained virtually untouched since the solar system's birth, offering pristine samples of ancient material. Studying their composition could unlock secrets about the building blocks of planets, even clues to how water and organic molecules arrived on Earth. Some scientists believe minimoons could one day serve as stepping stones for deep space exploration, low-gravity waypoints where we could test mining techniques or refueling missions without venturing too far from home. Yet the challenge of finding them is staggering. Most minimoons measure just a few meters across, reflecting so little sunlight they blend into the background noise of space. By the time astronomers spot one, it's often already on its way out, slipping through our fingers like cosmic quicksilver. Projects like the upcoming Vera C. Rubin Observatory aim to change that, scanning the skies with unprecedented precision to catch these evasive visitors in the act. What's truly humbling is realizing how dynamic our celestial neighborhood really is. Earth doesn't just move through space, it's constantly gathering and losing tiny companions, a dance of gravity and chance most of us never notice. So the next time you gaze at the moon, remember, it might not be the only one up there. Somewhere in the darkness, a minimoon could be silently circling, a temporary moonlet writing its brief chapter in Earth's endless skybound story. Pluto wears its heart on its sleeve, literally. When NASA's New Horizons probe raced past the dwarf planet in 2015, it revealed an astonishing sight, a sprawling, heart-shaped glacier nearly the size of Texas, stretching 1,000 miles across Pluto's frosty surface. This gleaming landmark, officially named Sputnik Planitia, isn't just a cosmic valentine, it's a geological powerhouse that reshaped the entire world beneath it. Sputnik Planitia is a vast basin filled with nitrogen ice so pristine it reflects sunlight like a celestial mirror. But here's the twist, that frozen heart isn't sitting where it should. Gravity maps revealed the glacier has an incredible hidden mass, likely a subterranean ocean lurking beneath the ice. That extra weight tipped Pluto's entire axis of rotation, literally causing the dwarf planet to roll over until the heart aligned with the gravitational tug of its largest moon, Charon. Imagine spinning a basketball on your finger, then slapping a bowling ball onto one side. It's that kind of planetary reorientation. What makes this glacial heart so dynamic is how it breathes. Pluto's thin nitrogen atmosphere freezes onto Sputnik Planitia's surface during the dwarf planet's long, frigid winters, then sublimates back into gas during its brief summers. This cycle carves the ice into surreal polygons, geometric fractures resembling dragon scales, each spanning miles. Winds race across these plains at mere miles per hour, but in Pluto's whisper-thin air, that's enough to push icy grains into drifting dunes. It's a world where even the gentlest breeze sculpts landscapes over millennia. The real shocker, Sputnik Planitia might be the solar system's ultimate recycling project. Some scientists believe the glacier sits inside the scar of a cataclysmic impact 4 billion years ago, a collision so violent it ejected enough material to form Charon. The basin then refilled with ice, turning trauma into beauty. Now it serves as Pluto's gravitational anchor, locking its motion in sync with Charon in an endless orbital embrace. This icy heart isn't just a pretty feature, it's a window into how even small, frozen worlds can harbor astonishing geologic activity. Beneath that nitrogen ice, tidal forces from Charon may keep Pluto's hidden ocean liquid, raising tantalizing questions about whether this distant outpost could host the ingredients for life. From reshaping a planet's spin to hiding secrets beneath its surface, Sputnik Planitia proves that in the cosmos, even the coldest hearts beat with unexpected fire. The night sky as we know it is on borrowed time because our galaxy, the Milky Way, isn't floating alone in the void. It's locked in a slow-motion death spiral with its colossal neighbor, the Andromeda Galaxy, and in about 4 billion years, these two titans will slam together in the ultimate cosmic merger. But don't panic, this isn't some apocalyptic smash-up. It's more like a grand celestial ballet where gravity weaves two galaxies into one without so much as a single star colliding. Right now, Andromeda is barreling toward us at 250,000 miles per hour, a speed that would cross the United States in under 10 seconds. But space is so vast that even at that velocity, the final clash won't happen for eons. When it does, the sheer scale of the collision is almost incomprehensible. The Milky Way and Andromeda each contain hundreds of billions of stars, trillions of planets, and enough dark matter to sculpt the very fabric of spacetime around them. Yet despite those staggering numbers, the distances between stars are so enormous that direct impacts are astronomically unlikely. Instead, galaxies pass through each other like ghosts, their stars sliding past one another unharmed. What will change is the night sky dramatically. As the merger unfolds over millions of years, the familiar band of the Milky Way will warp and distort. Andromeda, which today appears as a faint smudge in the constellation Cassiopeia, will grow larger and brighter, eventually stretching across the heavens. New constellations will form as stars from both galaxies mingle, their gravity weaving intricate patterns we can't yet imagine. The two supermassive black holes at their cores, our Sagittarius and Andromeda's even larger counterpart, will eventually spiral together, unleashing ripples of gravitational waves before merging into a single, monstrous void. The aftermath, a brand new galaxy nicknamed Milkdromeda by astronomers. This hybrid will be a sprawling, elliptical beast, its stars reshuffled into a chaotic new order. The orderly spiral arms we recognize today will be gone, replaced by a glowing, egg-shaped haze of stars. Any hypothetical future Earthlings looking up will witness a sky ablaze with unfamiliar suns, a testament to the universe's endless transformation. But here's the twist. While the galaxies merge, our solar system will likely be flung into a new orbit, carried farther from the galactic core by the gravitational chaos. Yet life here, if it still exists, might not even notice the upheaval. The real spectacle will be above. A slow-motion light show spanning generations where the heavens rewrite themselves before our eyes. It's a reminder that even the mightiest structures in the cosmos aren't permanent, they're just threads in an ever-changing tapestry, woven together by gravity's invisible hand. Imagine a star so cool you could reach out and touch its surface, not a blazing inferno, but something closer to a warm summer day. Meet the Y-class brown dwarfs, cosmic oddballs that blur the line between planet and star. These failed stars never gathered enough mass to ignite nuclear fusion in their cores, leaving them to smolder at temperatures as mild as 80 degrees Fahrenheit, cooler than your morning cup of coffee. While most stars scorch at thousands or even millions of degrees, these wanderers hover at room temperature, their surfaces barely warmer than Earth's deserts. Spotting these lukewarm giants isn't easy. Unlike traditional stars that blaze with visible light, brown dwarfs emit most of their faint glow as infrared radiation, the same type of heat you feel from a radiator. That means ordinary telescopes miss them entirely. It took cutting-edge infrared observatories like NASA, Spitzer, and WISE to peel back the cosmic curtain, revealing entire populations of these dim, drifting objects hiding in plain sight. Some drift alone through interstellar space, untethered to any solar system, while others orbit distant stars like shadowy companions. One of the coldest known, WISE 0857-4425, chills at barely 25 degrees Fahrenheit, cold enough to frost over on a bitter winter night. What makes brown dwarfs even stranger is how they defy classification. Too massive to be planets, yet too puny to be full-fledged stars, they occupy a celestial gray zone. Their cores may flicker with brief deuterium fusion, but it's a far cry from the sustained inferno of a sun. Over time, they fade like dying embers, cooling until they're nearly invisible against the cosmic backdrop. Yet even in their twilight, they're anything but boring. Some boast violent storms with hurricane-force winds whipping clouds of molten iron and sand into swirling tempests. Others harbor exotic atmospheres where it might rain liquid metals or scorching hot minerals, a far cry from Earth's water cycles. The hunt for these cosmic lukewarmers isn't just about cataloging oddities. Brown dwarfs could hold clues to some of astronomy's biggest mysteries, like how stars form at the lowest masses or whether rogue planets might outnumber stars in the galaxy. Their atmospheres serve as laboratories for studying extreme weather on worlds beyond our solar system. And let's not forget the tantalizing possibility of spotting one closer than we think, perhaps lurking unnoticed in the dark reaches of our own cosmic neighborhood. So the next time you step outside on a warm evening, look up. Somewhere in the vast dark, there might be a star quietly glowing with the heat of a campfire, a reminder that the universe has a way of turning our expectations upside down. While most planets spin like tops as they orbit the sun, Uranus plays by its own rules, rolling around our star like a drunken cosmic bowling ball. This ice giant tilts at a jaw-dropping 98 degrees, meaning its poles nearly point directly at the sun while its equator faces upward, turning the usual concept of seasons completely on its head. If Earth had this extreme tilt, our North Pole would stare straight at the sun for half the year, baking under perpetual daylight, while the South Pole plunged into 6 months of frozen darkness. What sent Uranus into this bizarre sideways spin? The leading theory points to cosmic violence, a cataclysmic collision with an Earth-sized object in the early solar system. Picture this: 4 billion years ago, when planets were still jostling for position, a rogue proto-planet may have slammed into Uranus with such force that it knocked the ice giant onto its side. The impact wouldn't just have altered its rotation, it could have vaporized part of Uranus's core, scattering debris that later formed its system of thin, dark rings. Supporting this theory is the fact that Uranus's moons orbit in the same tilted plane, like a set of dishes sliding sideways off a tipped table, evidence of a system-wide reorientation. But not all scientists are convinced a single impact explains everything. Some suggest gravitational chaos played a role, perhaps a series of smaller collisions, or even the tug of a massive, now-vanished moon that gradually pulled Uranus askew through tidal forces. There's also the curious case of Venus, which spins backward without a clear impact explanation. Could Uranus's tilt stem from some deeper instability in its formation, like a resonance with neighboring gas giants that amplified small wobbles into a full planetary roll? This extreme tilt creates surreal conditions. During Uranus's solstice, one pole bakes under continuous sunlight for 21 Earth years while the other freezes in endless night. When Voyager 2 flew by in 1986, it found Uranus's atmosphere oddly bland. But modern telescopes reveal raging storms appear as seasons shift, suggesting this quiet world has dramatic weather lurking beneath its hazy exterior. The tilt may even explain why Uranus radiates almost no internal heat, unlike Neptune, its twisted orientation possibly locking away primordial warmth in its interior. Uranus's sideways existence challenges everything we assume about planetary behavior. It's a reminder that the early solar system was a demolition derby where only the luckiest worlds emerged unscathed, and that even today, the cosmos keeps a few tricks up its sleeve to defy our expectations. Living in space doesn't just change your perspective, it literally stretches you taller. Astronauts floating aboard the International Space Station often return home with an unexpected souvenir, an extra 2 inches of height. Without Earth's gravity compressing their spines, the vertebrae in their backs gently expand like a coiled spring finally allowed to relax. It's the ultimate cosmic growth spurt, and it happens to almost every crew member within days of arriving in orbit. This spinal stretch isn't just a quirky side effect, it's a window into how brutally gravity shapes our bodies. On Earth, the constant downward pull squeezes the spongy discs between our vertebrae, flattening them over time. But in microgravity, those discs rehydrate and expand, lengthening the spine like an accordion unfolding. Some astronauts joke about finally reaching that childhood dream of being taller, at least temporarily. The change is so noticeable that NASA designed space suits with adjustable straps to accommodate the sudden vertical gain. But here's the painful twist: that extra height comes at a cost. Once back on Earth, gravity reclaims its grip with a vengeance. As the spine recompresses, astronauts often describe the sensation as being crushed by an invisible weight. The discomfort can last for weeks, with some comparing it to the ache of a severe back injury. Standing upright becomes exhausting, and many temporarily lose the curve in their lower spines, leaving them walking stiffly like action figures with locked knees. The implications go beyond temporary growing pains. Prolonged spinal expansion in space could lead to serious health risks like herniated discs or nerve compression. NASA solution: astronauts now spend hours harnessed into specialized resistance machines that simulate gravity's pull, trying to trick their bodies into remembering Earth's relentless tug. They also perform spine-stretching exercises to ease the transition back to terrestrial life, though nothing completely spares them the agony of returning to their original height. What's truly wild is how this phenomenon reveals the body's adaptability. Our spines aren't rigid pillars, they're dynamic structures constantly responding to their environment. In a way, every astronaut becomes a living experiment, proving that even something as fundamental as our height isn't fixed. It's a negotiation between biology and physics, one that shifts the moment we leave our planet's grip. So next time you wish you were taller, just remember, all it takes is a quick trip to orbit and a willingness to endure the crushing reunion with Earth afterward. Mars holds the title for the solar system's most extreme fire mountain, Olympus Mons, a volcano so massive it dwarfs every peak on Earth. Standing nearly 16 miles high, this colossal shield volcano is almost 3 times taller than Mount Everest, with a footprint so vast it could swallow the entire state of Arizona. If you stood at its base, the summit would vanish beyond the horizon, lost in the thin Martian haze. What makes Olympus Mons so staggeringly large isn't just its height, it's the way it formed. Unlike Earth's steep, cone-shaped volcanoes, which erupt violently and then collapse, Olympus Mons grew slowly over billions of years through gentle, repetitive lava flows. Picture a pot of honey spilled on a table, spreading outward in slow, sticky layers. That's how this Martian giant expanded, one oozing eruption at a time. Its slopes are so gradual you could hike them without realizing you're climbing a mountain, with an average incline of just 5 degrees, the secret behind its record-breaking size. Mars lacks the shifting tectonic plates that fragment Earth's crust. On our planet, volcanic hotspots constantly move as plates drift, creating chains of smaller volcanoes like Hawaii's islands. But Mars's crust stays locked in place, allowing magma to pile up in the same spot for eons. Olympus Mons became the ultimate lava fountain, its eruptions building upward and outward without interruption, free from the constraints that limit Earth's peaks. Another advantage: Mars's lower gravity. With just 38% of Earth's pull, Martian volcanoes can grow taller before their own weight crushes them. Combine that with thinner atmospheric pressure, and lava flows travel farther before cooling, spreading the mountain's base to a mine bending 370 miles wide. That's roughly the distance from New York City to Cleveland, all covered by a single, sleepy volcano. But here's the twist: Olympus Mons might not be entirely extinct. Recent satellite images reveal lava flows as young as 2 million years, a blink in geological time. While it's unlikely to erupt tomorrow, the mountain could still be simmering beneath its dusty surface, waiting for the next chapter in its epic story. This Martian titan isn't just a geological oddity, it's a testament to how differently worlds evolve. Without Earth's restless crust or crushing gravity, Mars built a volcano of impossible proportions, a silent giant forever watching over the red planet's rusty plains. While Earth's weather churns with chaotic storms, Saturn's North Pole boasts something far more precise: a hexagon so geometrically perfect it looks laser-etched into the planet's atmosphere. This 6-sided jet stream, wider than 2 Earths stacked side by side, has whirled in place for at least 40 years, possibly centuries, defying every expectation of how fluids behave in nature. Unlike the shapeless polar vortices we see on Earth, this structure maintains razor-sharp angles as it rotates, its sides each stretching nearly 9,000 miles long with near mathematical precision. The first close-up images from Voyager in the 1980s left scientists stunned. How could a storm, a churning mass of gas, hold such rigid, symmetrical form? Earth's polar vortices twist and warp with seasonal changes, but Saturn's hexagon remains locked in place like a cosmic gear, completing one rotation every 10 hours and 39 minutes with clockwork consistency. The winds along its edges scream at over 200 miles per hour, yet these violent currents somehow conspire to maintain perfect 60-degree corners, a phenomenon unseen anywhere else in the solar system. One leading theory suggests the answer lies deep beneath Saturn's clouds. The planet's rapid rotation, faster than Earth's despite being 9 times wider, may create stacked layers of atmospheric jets moving at different speeds. Where these layers shear against one another, standing waves could form, much like the hexagonal patterns seen in laboratory experiments with spinning fluids. On a small scale, this happens when you stir a cup of coffee. Tiny geometric ripples appear at the surface. Saturn's version is this effect scaled up to planetary proportions, with hydrogen and helium replacing coffee as the swirling medium. But here's the twist: while lab experiments can create short-lived hexagons in fluids, none maintain this stability. Saturn's version has outlasted multiple generations of researchers, its persistence hinting at deeper mysteries. Some models propose that the hexagon acts like a colossal version of a blocking anticyclone, a high-pressure system so stable it forces other weather patterns to flow around it. Others speculate about unseen dynamics in Saturn's interior, where electric currents or gravitational tides might imprint this pattern onto the atmosphere from below. What makes the hexagon even more mesmerizing are its nested features. Infrared observations reveal a towering central hurricane, its eye wall 30 times taller than Earth's worst tropical cyclones. This vortex spins independently within the hexagon's embrace, while smaller eddies dance along the geometric boundary like moons orbiting a planet. The entire structure even changes color with Saturn's seasons, shifting from golden hues in summer to a bluish tint in winter, as atmospheric chemistry responds to shifting sunlight. This isn't just a meteorological oddity, it's a masterclass in fluid dynamics. The hexagon challenges our assumptions about how energy dissipates in planetary atmospheres, offering clues about everything from Jupiter's roiling storms to weather patterns on distant exoplanets. It stands as a reminder that nature's rulebook is thicker than we imagine, and somewhere beyond Earth, a perfect geometric storm has been turning, untouched, for longer than our telescopes have existed to witness it. The moon might seem like a silent, lifeless world, but beneath its dusty surface lies a hidden restlessness: moonquakes. These lunar tremors can shake the ground with surprising force, some reaching up to 5.5 on the Richter scale, strong enough to rattle dishes off shelves back on Earth. Unlike earthquakes, which rumble from shifting tectonic plates, moonquakes stem from entirely different cosmic forces, revealing a world far more dynamic than its tranquil appearance suggests. Some of the strongest moonquakes trace back to the moon's strained relationship with Earth. Our planet's gravity tugs unevenly on the lunar crust, stretching and squeezing it like a rubber ball caught in Earth's tidal grip. These deep moonquakes originate up to 700 miles below the surface, where the strain builds until the rock finally fractures. Apollo astronauts left seismometers behind during their missions, and the data they collected shows these quakes can last 10 times longer than earthquakes, sometimes shaking the moon for over an hour. Imagine standing on the lunar surface, feeling the ground tremble beneath your boots in slow, eerie waves, with no atmosphere to muffle the vibrations. But tidal forces aren't the only culprits. Meteor impacts send shockwaves rippling through the moon's brittle crust, triggering impact quakes that echo across the barren landscape. Even the extreme temperature swings from scorching 260 degrees Fahrenheit in sunlight to minus 280 in shadow. cause the ground to expand and contract violently enough to produce thermal quakes. The Moon's surface is essentially a giant, cracking pavement under the relentless stress of deep space conditions. What makes moonquakes especially dangerous is the Moon's lack of erosion. On Earth, frequent quakes and weather wear down jagged terrain, but the Moon preserves its fractures like a cosmic fossil. Over billions of years, these cracks have accumulated, leaving the subsurface riddled with faults and unstable rubble zones. For future Moon bases, that's a serious problem. A strong moonquake could destabilize habitats, fracture solar panels, or even collapse underground lava tubes that colonists might rely on for shelter from radiation. Engineers designing lunar structures will need to account for these tremors, perhaps anchoring buildings to bedrock or using flexible materials that sway rather than shatter. The discovery of moonquakes forces us to rethink the Moon's geologic personality. It's not a dead relic, it's a world still responding to the cosmos in ways we're only beginning to understand. Every tremor is a reminder that even in the stillness of space, nothing stays perfectly still. Comets streak across the solar system like celestial road trips, their shimmering tails stretching millions of miles behind them. But here's the cosmic curveball. No matter which way a comet is moving, its tail never streams behind it like a scarf in the wind. Instead, it always points directly away from the sun, defying common sense in one of the universe's most elegant demonstrations of invisible forces at work. Take Halley's Comet, for example. When it swings around the sun, its tail billows outward like a cosmic windsock, whether it's approaching or retreating from our star's fiery embrace. The secret lies in the sun's relentless breath, solar wind. This isn't just light streaming into space, it's a supersonic river of charged particles racing outward at nearly 1,000,000 miles per hour. When sunlight heats a comet's icy nucleus, vaporized gas and dust erupt from its surface. But instead of drifting lazily behind the comet's path, these materials get swept up by solar wind and radiation pressure, shoved irresistibly away from the sun like leaves caught in a celestial hurricane. The result, a tail that acts less like a trailing flag and more like a compass needle, perpetually aligned against the solar gale. Halley's Comet demonstrates this phenomenon spectacularly. As it nears the sun during its 76-year orbit, solar energy transforms its frozen nucleus into a glowing fountain of gas and dust. But the comet's tail doesn't simply follow its motion, it pivots in real time, adjusting its angle as the comet rounds the sun. Picture a speedboat making a sharp turn while its spray keeps blasting backward from the engine. Halley's behaves similarly, its tail bending along an invisible line dictated by solar forces rather than the comet's trajectory. What's astonishing is that comets often sport two distinct tails, each betraying a different solar interaction. The ion tail, made of electrified gas, is the more obedient of the two, pointing rigidly away from the sun as charged particles lock into the solar wind's magnetic grip. The dust tail, heavier and more sluggish, curves slightly as individual grains resist the push of light pressure, creating a gently arcing trail that still broadly obeys the solar directive. Together, they form a dynamic duo of cosmic signage, their orientation broadcasting the sun's influence across the solar system. This isn't just a quirky rule, it's a clue to the sun's domain. Solar wind carves out a vast bubble called the heliosphere, within which every comet becomes a weather vane, its tail mapping the invisible currents of our star's fury. Ancient astronomers once saw comets as omens, their tails scribbling cryptic messages across the sky. Today, we recognize them as nature's own physics experiments, proving that even in the vacuum of space, nothing moves entirely freely. The sun's reach extends far beyond its light, and every comet's tail is a silent testament to that power, a flame forever bending away from the fire that birthed it. The universe isn't just a silent void, it's a symphony, and black holes are the deepest bass singers in the cosmic choir. In the heart of the Perseus cluster, 250 million light-years away, a supermassive black hole has been humming a single, eerie note for billions of years, a B-flat 57 octaves below middle C, so low it's beyond human hearing. This isn't science fiction. It's raw astrophysics captured by NASA Chandra X-ray Observatory in the form of rippling pressure waves radiating through scorching intergalactic gas. How does a black hole, an object so dense not even light can escape, produce sound? The secret lies in its appetite. As this cosmic monster devours surrounding matter, it doesn't do so quietly. Energy erupts from its accretion disk in violent outbursts. These explosions slam into the galaxy cluster's superheated gas like a hammer striking a drum, sending pressure waves rippling outward at frequencies measured in million-year intervals. The result is a sound wave with a wavelength so vast it could wrap around our solar system 100 times over, resonating through space like the world's slowest, deepest church bell. To hear this cosmic dirge, scientists had to speed it up way up. The original frequency is 1 oscillation every 10 million years, but when boosted by 57 octaves, that's multiplying the frequency by over 100 quadrillion times, it transforms into something hauntingly audible. The processed sound is a drone, a subterranean hum that vibrates in your bones more than your ears, like standing next to a pipe organ the size of a galaxy. What's astonishing isn't just the sound itself, it's the scale of its influence. Those pressure waves do more than sing, they shape the cosmos. As they propagate, they prevent the cluster's gas from cooling and collapsing into new stars, effectively putting the brakes on galaxy growth. The black hole's song isn't just a curiosity, it's a regulatory force, a gravitational feedback loop that keeps the universe from burning out too fast. This discovery shatters our assumptions about black holes as silent killers. They're not just voids, they're active participants in the cosmic orchestra. Their voices too deep for us to naturally hear but powerful enough to conduct the evolution of entire galaxy clusters. So the next time you gaze at the night sky, remember, the darkness isn't mute. It's vibrating with frequencies older than life itself, a soundtrack written in the language of gravity and time. We've all grown up drawing the sun as a bright yellow circle in the sky, but here's the cosmic reality check. Our star isn't yellow at all. The sun, when seen outside Earth's atmosphere, is a crisp, clean white. That golden glow we associate with sunrise and sunset, that's just our planet playing tricks on the light, the magic, or rather, the physics happens in Earth's air. Sunlight arrives here as a blend of every color in the visible spectrum, which together appear white to our eyes. But as those rays slice through the atmosphere, they collide with nitrogen and oxygen molecules. Shorter wavelengths, blues and violets, get scattered wildly in all directions, which is why the sky looks blue during the day. The longer wavelengths, reds, oranges, and yellows, plow straight through with less resistance. By the time sunlight reaches your eyes, the scattering has filtered out so much blue that what's left skews yellow. It's the same reason distant mountains often appear hazy and blue. The more atmosphere light travels through, the more the shortest wavelengths get hijacked. This isn't just theory. Spacecraft like the Solar Dynamics Observatory have captured the sun in its true, unfiltered glory, a blazing white disk with no hint of yellow. Even astronauts aboard the International Space Station confirm it. Step outside Earth's atmospheric bubble, and the sun sheds its golden disguise, revealing itself as a stark white sphere against the black void. Only during sunrise or sunset, when sunlight slants through the thickest layer of atmosphere, does the scattering become extreme enough to turn the sun deep orange or red. But if the sun is white, why do we perceive its light as warm-toned? Evolution wired our brains to compensate for the blue scattered sky, subtly shifting our color balance toward yellow to maintain visual consistency. It's the same reason we don't notice the reddish tint of incandescent bulbs after a few minutes. Our eyes adapt. Even photographs of the sun taken from Earth's surface often get white balance to match our expectations, reinforcing the illusion. The implications stretch beyond trivia. This color shift affects everything from solar panel efficiency to climate models. Scientists studying sunlight's intensity must account for atmospheric scattering to measure the true energy reaching Earth. Even space telescope designers use the sun's real white hue to calibrate their instruments. So next time you squint at the sky, remember, the sun isn't the butter yellow orb of childhood art. It's a raging white sphere, its light filtered and bent by the thin blue shell of our planet's air. A star's true face hidden in plain sight. Imagine a world where rain doesn't bring life, it brings shards of molten glass, slicing sideways through searing winds at over 5,000 degrees Fahrenheit. Welcome to HD 189,733b, an exoplanet so brutally alien it makes every sci-fi hellscape look tame. This cobalt blue gas giant, orbiting dangerously close to its host star, has weather patterns ripped from nightmares, hurricanes with winds clocking 4,500 miles per hour, fast enough to outrun a bullet 7 times over, whipping tiny silicate particles into a deadly glassy tempest. The physics behind this glass rain is as beautiful as it is terrifying. The planet's atmosphere, superheated to nearly half the temperature of the sun's surface, vaporizes silicate minerals, the same stuff that makes up sand on Earth. As these vaporized minerals rise into cooler layers, they condense into microscopic droplets of molten glass, only to be caught in the planet's supersonic jet streams and hurled sideways in horizontal storms. Unlike Earth's gentle raindrops that fall vertically, these glass particles shoot across the sky like hypercharged shotgun pellets, propelled by winds that could strip flesh from bone in seconds. What's truly unsettling is how deceptively serene HD 189,733b appears from afar. Hubble Space Telescope observations revealed its deep azure hue, reminiscent of Earth's oceans. But this blue comes not from water, but from sunlight scattering off suspended silicate particles in its upper atmosphere. It's a cruel cosmic joke, a planet that mirrors our ocean's color while harboring storms that would vaporize a spacecraft before it could scream Mayday. Scientists compare HD 189,733b to a bigger, hotter Jupiter, but with a twist. Jupiter's great red spot, for all its fury, is a picnic compared to this exoplanet's permanent maelstrom. There are no calm days, no breaks in the violence, just an endless, scorching gale where the very sky is a weapon. The glass rain never hits the ground. It likely evaporates back into the lower atmosphere, only to rise and condense again in a perpetual cycle of destruction. This isn't just a spectacle of extremes, it's a window into how diverse planets can be. Our solar system's weather, from Martian dust devils to Saturn's hexagon storms, suddenly seems quaint. HD 189,733b forces us to expand our imagination. If glass rain exists, what other surreal meteorological horrors lurk among the stars? Diamond hailstorms on Neptune, liquid metal cyclones on super-Earths. The universe, it seems, has a flair for the dramatic, crafting worlds where the weather itself defies the limits of human imagination. Want to slow down time, skip the pricey creams, and just book a ticket to space because, according to Einstein, astronauts are practically stealing extra milliseconds from the universe? Here's the mind-bending reality. Every second you spend orbiting Earth on the International Space Station makes you age ever so slightly slower than people on the ground. Over a typical 6-month mission, astronauts gain about 0.005 seconds of extra life thanks to relativity. Not enough for a fountain of youth, but enough to prove Einstein was right in the weirdest possible way. This cosmic quirk stems from time dilation, a consequence of Einstein's theory that time isn't universal, it stretches and compresses depending on speed and gravity. The ISS zips around Earth at 17,500 miles per hour, moving fast enough that time actually ticks slower for astronauts compared to those of us stuck in gravity's grip. Meanwhile, Earth's gravity, stronger at the surface than in orbit, tugs time in the opposite direction, slowing clocks on the ground relative to the station. The effects cancel out somewhat, but not completely. Speed wins, leaving astronauts with a tiny temporal bonus. But before you sign up for a spaceflight to cheat aging, consider this. To notice any real difference, you'd need to live aboard something like the ISS for decades. Even Scott Kelly, who spent nearly a year in orbit, only gained about 0.01 seconds over his twin brother Mark. The real winners, GPS satellites, their onboard clocks run faster by 38 microseconds daily due to weaker gravity in medium orbit, and engineers have to correct for this or your phone's maps would drift by miles every day. What's wild isn't just the science, it's how relativity warps our intuition. We think of time as rigid, but the universe treats it like taffy, twisting it around massive objects and high speeds. Black holes take this to extremes. Orbit one at the right distance, and a few hours for you could mean centuries back on Earth. The ISS effect might be minuscule, but it's proof we're all surfing the ripples of spacetime, whether we feel it or not. So while astronauts won't return looking younger, they do come back as living proof of a truth far stranger than fiction. Time is negotiable, and the universe keeps its books in more than one currency. Einstein's legacy isn't just equations, it's knowing that every tick of the clock is a little softer, a little more flexible than we ever imagined. Earth might seem to have a monopoly on lunar companionship, but there's an unassuming space rock out there playing an intricate game of cosmic tag with our planet Cruthon. This 3-mile-wide asteroid doesn't orbit Earth like the Moon, yet it's locked into such a precise gravitational dance with us that scientists call it a co-orbital companion. Every 385 years, Cruthon completes a mesmerizing horseshoe-shaped path around the Sun, sometimes lagging behind Earth, sometimes racing ahead, but never straying too far from our planet's gravitational embrace. What makes Cruthon's orbit so special is how it defies simple categorization. Most asteroids follow predictable elliptical paths, but this one traces a celestial spiral that, when mapped over centuries, resembles a sprawling horseshoe. For about 200 years, Earth gently tugs Cruthon forward, accelerating it into a slightly faster orbit. Then, as the asteroid catches up from behind, our planet's gravity flips the script, dragging it back into a slower trajectory. The result, a graceful, looping chase where Cruthon never quite laps us but never falls too far behind either. This orbital ballet isn't unique to Earth. Other planets have co-orbital partners too, but Cruthon's relationship with us feels almost intentional. At its closest, it drifts within 12 million miles, about 50 times the Moon's distance, close enough for Earth's gravity to nudge its path without ever fully capturing it. Some astronomers joke that it's Earth's quasi-moon, though technically it's always orbiting the Sun, not us. The Moon, by contrast, is tidally locked to Earth, forever bound to our gravitational sway. The real marvel is how stable this arrangement is. Computer simulations suggest Cruthon has been tracing this intricate pattern for thousands of years, and it could keep doing so for millennia more. Unlike other near-Earth asteroids prone to chaotic orbits, Cruthon's path is a masterclass in gravitational harmony, a testament to the delicate balance of celestial mechanics. It doesn't pose a collision risk, its orbit is too carefully choreographed for that, but it serves as a reminder that Earth's gravitational influence extends far beyond the Moon. So why isn't Cruthon common knowledge? Partly because its discovery in 1986 flew under the radar, overshadowed by flashier space news. But also because it challenges our idea of what counts as a cosmic companion. We're wired to think in binaries, moons or not moons, but the universe loves ambiguity. Cruthon exists in the gray area, a rock that's neither moon nor mere passerby, but something in between. The next time you look up at the night sky, remember, Earth's gravitational family might be bigger than you thought. Hidden in the void, a silent partner traces its slow, elegant arc around the Sun, forever linked to us in an orbital waltz older than recorded history. The Moon may be our primary dance partner, but truth proves even the loneliest planets have company if you know where to look. If you zoomed out far enough to see the universe on its grandest scale, you wouldn't find galaxies scattered randomly like sprinkles on a cupcake. You'd see a vast, intricate spiderweb stretching across billions of light years. This cosmic web, the largest known structure in existence, isn't made of silk but of dark matter filaments thinner than threads of smoke, woven between unfathomably empty voids. These invisible tendrils form the universe's hidden skeleton, guiding galaxies into sprawling clusters along their glowing intersections like pearls strung on a necklace. The eeriest part, we can't even see most of it, dark matter. That mysterious substance making up 85% of the universe's mass doesn't emit light or interact with ordinary matter. Its presence is only betrayed by its gravitational grip on galaxies, bending space itself into this intricate lattice. Supercomputer simulations reveal how these filaments emerged from the primordial soup of the Big Bang, where tiny quantum fluctuations snowballed into gravitational wells over billions of years, funneling gas and dust into the web's sticky strands. What brings this shadowy architecture to life are the luminous rivers of hot gas coursing along the filaments, some reaching temperatures of 10 million degrees. When galaxies form at the web's nodes, their supermassive black holes pump energy back into these channels, creating feedback loops that regulate star formation across millions of galaxies. It's as if the universe built its own circulatory system, with dark matter as the bones and glowing plasma as the blood. The voids between filaments are another marvel. These cosmic deserts can span hundreds of millions of light years, so empty that if you stood in one, the night sky would appear nearly black. No stars, no galaxies, just the faint glow of the cosmic microwave background. Yet even these apparent wastelands play a role, their low-density environments allowing the web's structure to stretch and evolve like a living organism. This isn't just a static blueprint, it's a dynamic, ever-changing network. Recent observations show galaxies flowing along filaments in a slow-motion river called dark flow, pulled by gravitational forces we're only beginning to map. The cosmic web binds everything together in a dance of dark and light, proving that even the grandest structures emerge from the universe's simplest rules. So next time you gaze at the stars, remember, each pinpoint of light is just one stitch in a tapestry vaster than human imagination can grasp. From diamond planets where rain comes in the form of glittering gemstones to black holes humming deep cosmic lullabies, the universe has proven time and again that reality outshines even our wildest sci-fi dreams. We've explored a superstorm shaped like a perfect hexagon, a planet where glass rains sideways at thousands of miles per hour, and even a star so cool you could touch its surface without burning your hand, if you could somehow survive its crushing gravity. Each of these cosmic oddities forces us to rethink what we know about the rules of physics, the nature of time, and the sheer creativity of the universe. Take a moment to let that sink in. Every single one of these phenomena exists without any human intervention. No special effects, no exaggerations, just the raw, unfiltered spectacle of a cosmos that refuses to be boring. Think about the diamond planet 55 Cancri E, where the very ground beneath your feet would be worth more than all the wealth on Earth combined, if you could somehow survive its 4,000-degree heat. Or the black hole in the Perseus cluster, singing a note so low it vibrates across millions of light years, conducting the very fabric of galaxy clusters like a cosmic maestro. And who could forget Saturn's vanishing rings? Those iconic bands of ice and dust, the jewels of our solar system, are younger than the dinosaurs and might fade entirely in another cosmic blink of an eye. Or Mercury, the scorched world that somehow hoards ice in its shadowy polar craters, defying logic with every frozen molecule. Even Earth isn't exempt from the weirdness. Our planet sneaks extra moons without us noticing, tiny asteroids caught in a gravitational dance so delicate it's lasted millennia. So now it's your turn. Which fact left you staring at the screen in disbelief? Was it the raspberry-scented gas cloud floating near the Milky Way's heart? Or maybe the way astronauts return from space just a tiny bit taller, only to have Earth's gravity crush them back down to size? Drop your favorite in the comments. We want to hear which cosmic wonder blew your mind the most. And if you're hungry for more universe-shaking revelations, hit that subscribe button. Space is full of secrets and we're just getting started. Until next time, keep looking up because out there, the impossible is just another Tuesday.